Hey, this is Chris, and we're taking a look at our third video in our torque series. In this case, we're going to be looking at a scenario where we have a distance that's being asked for. So before, we just had to figure out, okay, which way is this seesaw going to tip with all of the given information to solve for both torques. So we basically, in our last video, and if you haven't watched it, check it out, but our last video we were looking at, okay, what direction would this rotate? So in this video, it's going to be different. This would be the type of scenario where we are asked a question where they want to know what is required to keep the seesaw balanced, or sometimes you might hear the word static, which means it's not moving. Or they might even tell you, like where are these torques going to be equal? Or where is it going to be in a state of equilibrium? So those are the types of words that you would see used in a question that's asking about these calculations. But basically what we're looking at here is going to be a different kind of missing variable. So here, our missing variable is going to be R2. It's this distance. And so this is going to be the same calculation for that first torque. That's torque in the positive direction. We're given a mass of 10, R of 6. We plug it in, 6 times 10 times 9.8, so R times F1, or R times mg, would be 60 times 9.8, which is 588. Sine of 90 is equal to 1. That's a positive 588 for that torque. So we know that value of 588. But then we don't know what this R value is for the other torque. But what we do know is that the sum of these torques, if it's balanced, or if it's in a static situation, or if it's in equilibrium. So sum of the torques is going to be 0. They have to cancel out, which means that torque 2 here is going to be a negative 588, right? It has to counter that first torque, which basically means magnitude-wise it's going to be 588. And the negative just indicates that we are, like we said here, we're moving in the clockwise direction. So let's plug in everything we know and see if we have enough to solve for R2. So here, zoom in a little bit on this because now we only care about this equation for the moment. So here, our R value, we don't know. That's what we're solving for. Our mass is 30. Our acceleration due to gravity is still 9.8. Our sine is still 90. Those values are not changing. So this mass, to apply a torque, it still has a downward force due to gravity. And we're solving for R, which means we're solving to figure out where would you place this mass on this seesaw or on this balance in order for it to remain level. And here, when we go ahead and do that calculation, so to simplify a little bit, I'm gonna move this over a touch, but we'd have 588. And then we have 30 times 9.8 times sine of 90. Remember that sine of 90 is equal to 1, so it's just 30 times 9.8, which would be 294, times R2 would equal 588. Divide by 294, we would get 2 equal to R2. So basically, in this question, that means that this distance here is 2 meters. That's going to be our answer to this question. In order for this balance to remain static, in order for this seesaw to not move, we would have to place our second mass of 30 kilograms, a distance of 2 meters to the right of the fixed point, or to the right of the fulcrum, in order to achieve balance. So this is just another application of torque, but in a question worded slightly differently. Stay tuned and we'll dive into even more examples in our remaining videos in our torque series. Thanks.